So my I'll pull this from memory. I think that because I just did it. Number 33 is perfectly in line with what you should be capable of doing on your test. I see no difficulty in assigning it. You might find difficulty in doing it, but I don't have any problem with it as a question relevant to what we've been talking about in class. So consider that there's a box on a ramp, and the box is being pulled up the ramp by a tether or a rope. That is, I interpreted the problem where the rope is aligned with the ramp. Does that seem how you guys interpreted the problem too? We don't know the amount of tension here, but we do know that the box has a mass of 10 kilograms and the ramp has an angle of 30 degrees. So they would like us to figure out the tension in the rope necessary to pull the box up the ramp at a constant velocity, knowing that there is a coefficient of kinetic friction of, I believe, 0.3 between the block and the ramp. Is that the problem? All right. So let's start. I'm going to start with the free body diagram. And I'm just going to draw the free body diagram superimposed right over the block. So you'll want to mute that. If I hear myself in the background, I won't believe that I have the rock star voice that I believe I do. I'll hear my real voice. And I know how terrible it sounds. It's all nasally, and I believe it's like deep and resonant. And it is not. And on video, it's even worse. So I'm not even sure why I record this garbage. But here we go. I would say the next force I would probably draw is weight. Straight down. There is a normal force because we're in contact with the surface. And that force should be drawn so that it is perpendicular to the surface, like so, and should be long enough so that it counters the amount of weight that's going into the surface. That's a normal force. And we have frictional force. Don't really know how big it is, but we know the combination of the frictional force and the weight down the ramp is going to be equal to 0 in part A. So that's kind of what I've drawn. These are the 4 forces that act in the system. I'm going through my list of forces. Any questions about those 4? All right, so my next step is to draw a coordinate system. And I hope this isn't a big stretch, but I'm going to align my coordinate system with the ramp. We talked about why for a couple of reasons, but this problem actually, we want to set it with the ramp for 2 reasons. The first is that it lines up with 3 of the 4 forces. And the second reason is because in part B, we are going to be accelerating up the ramp. And so make this the positive x direction, and you'll be happiest. And this one is the positive y direction. I'll make this negative and this negative. That makes this 30 degrees. And I'm probably done talking about why that's 30 degrees. Memorize it if you don't know why. That's the one that lines up with the normal force. I have to break this up into 2 components. There's a component that is in the y direction and a component that is in the x direction. The right angle goes here. You guys draw it in wrong places, and I've tried to correct you, but at this point, it's on you. This is going to be mg cosine 30, and this one's going to be mg sine 30. Now, all of this stuff I'm doing is not a part of the free body diagram. The free body diagram was just the original 4 red arrows. I am finishing up the set of steps necessary to solve the problem, which is to take any off-axis forces and find their components so they are now on the axes that I drew. So I think we're done with those things. We have converted all of our forces into components that are necessary. Every force now lines up in either the x direction or the y direction. Any questions? Yep.
On the test, would you want us to draw just the free body diagram and then to solve, draw it again with the coordinate system?
There's a part of the test where you have to draw a free body diagram that cannot have anything on it. So yes, there'll be a part of the test where you'll have to do that. All right, so now we have to apply Newton's laws. And part A is a first law problem. So net force equals 0. Now, net force in the x direction equals 0. Net force in the y direction equals 0. Again, I'm just applying my set of steps. So now I need to add up all the forces in the x direction, taking into account their direction, and set them equal to 0. There are 3 forces in the x direction: friction, the portion of the weight, and the tension. Those 3 forces are in the x direction. They should appear here. So tension is positive, mg sine theta is negative, friction is negative, and that should sum to be equal to 0. Questions? All righty. Add up all the forces in the y direction, taking into account the direction, and set them equal to 0. There are 2 forces in the y direction. There's normal, and there's mg cosine 30. Those are the only 2 forces that are pointed in the y direction. So normal is positive, minus mg cosine 30, bless you, is negative, and set that equal to 0. That's it. That's Newton's laws. That's as far as I can go with Newton's laws. The problem asked us, I believe, to find the tension. So in order to find the tension, I will point out the only way I can determine the tension is if I have m, g, the angle, and friction. I don't have friction. I have mg and sine theta. That's easy. But I don't have friction. However, friction is defined as mu times the normal force. And I know they gave me mu. I wrote it down. Which means I could figure out friction if I know the normal force. To know the normal force means I need to say, all right, normal equals mg, 10 times 10 times the cosine of 30. Seems to me I can figure out the normal force. 10 times 10 is 100 times the cosine of 30. It's got to be 86.6 newtons. That's the normal force. Again, if I know the normal force, I know the frictional force. Friction is 0.3 times 86.6. So I think that's got to be 26. About right? Third of that. So 26 newtons is friction. So now I think I finished. I have tension equals mg sine 30 plus 26. 10 times sine 30 is 50, plus 26 is 76 newtons. That should be the tension. All right. Not terrible. Questions about that? It's easy when I do it. It's going to be harder tomorrow. What?
When I do 10 times sine 30, like my calculations are all just. Oh wait, it's cosine.
Sine 30 is a half, so it's you. I mean, you can check to see if your calculator's in degrees or radians. Somebody in here should be nice enough to say that tomorrow before the start of the test, because I'll forget. Yes, ma'am.
Are we going to be able to use our little,
Nope. I will be giving you an equation sheet tomorrow, and there's the AP1 equation sheet. If you want to see it, type in AP1 equation sheet, and you'll probably get a solid PDF hit on that. But it has 3 of the 5 motion equations already on it.
I was talking about the new, I don't know the
It'll have friction equals mu times the normal force on it. It'll have Newton's laws on it. Now,
is it going to be that
let's finish this. That's just part A. There's still part B. So part B has you redo the entire problem, but this time the net force doesn't equal 0, it equals ma. They want it to accelerate. This isn't a huge difference. You do not have to redo the whole problem. The only thing that has changed is that the net force does not equal 0. the net force now equals MA, which is 10 times, I think it accelerates at 0.5 meters per second squared. So it's not a big change. Your force has to be unbalanced by what appears to be 5 newtons. So I'm going to be adding all of that to the other side, but the other side isn't 0 anymore. The other side is 10 times 0.5. So it's not a huge difference. It's not going to be 76. It'll be 76 plus 5. So it looks like the new tension is 81 newtons. Isn't that what the acceleration is? Yep. From the textbook. Part B, question 33. There. Test question? Sure. Absolutely. I have absolutely no qualms about giving this tomorrow. I don't think there's anything in here. Now, I think that there's ways to tweak this problem to make it harder. I'm not attempting to do that, though. I think if you can work this problem from beginning to end, I think you're in good shape for tomorrow. Yes, sir? Yeah, well, I think when we're looking at it, we chose the direction of the axes, correct? So I don't think the box is going to accelerate this way. Do you? This doesn't seem reasonable. So the box seems to be pretty constrained to move only along this axis. So yeah, if that's why we do it this way, so that we will make sure we get at least one of these where the net force has to equal 0. All right. Are there any other questions on the practice test or the homework to which I can speak now? We have more time. Yes, sir?
Can you do number 6 on page 111?
Probably. So this is number 6 in the homework. There's a box hung by a rope. And there's a knot here where another rope goes off at some angle. And another rope goes horizontally. This looks famously like one we looked at. We are given that this angle is 53 degrees. So the box has a weight of 400 newtons. So if I was to turn this into a free body diagram, then there's 400 newtons downwards. There's got to be a tension upwards, and just this portion of the tension has to be 400 newtons. All right, that's the only rope that pulls upwards. And then there's got to be another tension this way to balance the fact that I'm pulling up at an angle. So this is T2, this is T1. Any questions about that? I think a coordinate system aligned with the 2 existing weight tensions is the right way to go. So I'm going to use that coordinate system. And I'm going to break the tension 2 into 2 component vectors. So that I'll have T2 cosine 53 and T2 sine 53. Any questions there? All right. Net force has to be 0. So net force in the x direction has to be 0, and net force in the y direction has to be 0. In the x direction, I have T1 equals T2 cosine 53. I'm just kind of jumping ahead. I'm not going to put T1 minus T2 cosine 53 equals 0. They have to be equal. Am I all right with that? In the same way that 400 has to equal T2 cosine 53 degrees. Is that good? That's the up and down ones. Sine. Good, good, good. Making sure somebody's paying attention. All right. Now, we need to figure out T1 and T2. I'm going to show you a trick. I'm not sure if you'll think it's a trick, but I think it's a trick. Consider just for a minute that I have T2 cosine here and T2 sine here. You guys see that? I'm just going to grab that and bring him right down there. Whenever you have something times the sine and something times the cosine, consider doing this. It'll save you a ton of time. Divide the two equations. I'm dividing the left side by T1, and I'm dividing the right side by T2 cosine 53, because I'm allowed to divide the same thing on both sides of an equation. If I do that, this automatically eliminates T2. Right? Eliminates it right away. It also, because it's sine and cosine, turns that into tangent 53 equals 400 divided by T1. It's just a faster way to substitute. You could have done the substitution if you wanted, but I'm going to use this. Since we did this problem already in class, I thought it'd be worthwhile using it as a learning experience. So this means that 400 equals T1 tangent 53, or T1 equals 400 divided by tangent 53. So that's how much T1 equals. Once you get that, you can go back and figure out T2. That's about all I want to do on that one. It's not particularly interesting. Does that mean it's not testable? It's testable. Multiple choice, maybe. The part about this problem before number 4. Which one?
Well, just one. I have a question about that one.
Consider all the forces acting on the block. What can be said about the forces acting on a block and their effect on the motion variables regarding the block? Be sure to explain how Newton's first and second law factor into the effect on the forces and the motion variables. Also, in your explanation, be sure to indicate if any of the motion variables are changing and how they are changing. But just so you know, when I gave this last year, tons of students don't get all the points here because they don't answer all the questions. They answer what they want to answer, and then they screw up the rest of the test. There's a lot of things you're asked to address here, and each one of them is worth a point. So if you don't address them, you only address maybe the top level question, you lose, 5-7 points because you won't answer the question. So there's several things that should be talked about here. First, this is a Newton's second law problem because there are an unbalanced group of forces acting on the system. Although the forces are balanced in the y direction, they are not balanced in the x direction. So when you're asked to speak to Newton's first and second law, you should probably say that the system is balanced in the y direction, so the block does not accelerate up or down, but that it's not balanced in the horizontal direction. The box is going to slide across the floor, and it's going to accelerate due to the unbalanced force acting on the block. So it says, what can be said about the forces acting on the block and their effect on the motion variables? Well, there is a portion of the tension that is horizontal. Because of that, and because of Newton's second law, the block is going to experience an acceleration. What does that mean? Because it asks you, also in your explanation, be sure to indicate if any of the motion variables are changing and how they are changing. Well, the initial velocity is not changing. That's where it started. But clearly, the velocity of the block is changing. It is increasing. Why? Because it's accelerating. And its displacement away from the origin is changing. Why? Because it's accelerating. So both of those motion variables are changing. And the acceleration is changing. It's not constant. That's being pulled to the right. The direction of the tension is changing. Therefore, the acceleration is changing. The acceleration is decreasing. So as it gets closer and closer to the end of the ramp, of the end of the platform, the acceleration is going to be getting smaller and smaller and smaller. You don't really have to address time. Time's always increasing. All right, so skip 2 and 3 and talk about 4?
For the top-looking angle, what angle is that?
I can only see one angle. This angle. The angle between the pulling force and the horizontal. That angle is changing. It's becoming greater all the time.
So like, well, okay, then we can just take
So you guys missed the fact that you should have asked about number 3, which tells me that you are not prepared for tomorrow's test. Because what did you say, number 3? The reason I bring it up is all of those things affect it. Stickiness being pretty much a big one, but all of them affect it. And if you didn't know that and you're not paying attention to it, you're going to really screw it up. It says which property, the angle of the rope, the pulling force, or the stickiness of the surface would have the most impact on determining which outcome from the above would occur. I don't think you know the answer to this question unless you worked it out. I think it's a little brazen that you think this question 4 is actually the easier of the questions. So when we take a look at this one, Describe the motion of the box during the time that the box is receiving the 50 Newton force. If it's accelerating, please find the magnitude and direction of the acceleration. Is there anybody who needs me to draw a free body diagram before I do that? There are, I believe, 3 forces acting on the box during this time. There's a pushing force given to us. There is the weight of the box. And there is a normal force. Uh, 30 degrees. So we are told that the pushing force is 50 newtons and the block has a mass of 15 kilograms. So I'm going to skip some steps since nobody really was asking very much. So this has got to be a 50 cosine 30. And this one downward has to be 50 sine 30. Any questions about that? All right. So question 3, describe the motion of the box during the time the box is receiving 50 Newton force. It is accelerating. Why? Because net force has to equal ma. It's unbalanced sideways. So what is the amount of force that is sideways? 50 cosine 30 degrees. And that has to equal 15 times a. That would be the size of the acceleration. That's 43 divided by 15, so it's probably close to 3 meters per second squared. It's a little less than 3, but that's a good start. Any questions? All right. Question 2 is required for question 4. So I'm just going to speak to it anyways because it seems like we're getting a lot of questions out there. So I've got normal up minus weight minus 50 sine 30 equals 0. 50 sine 30 is 25, and the box is 15 kilograms. So that's 150. So it looks like the normal force equals 175 newtons. Any questions there? Question number 4 is a motion equation. Delta x is 10. Initial velocity is 0. Final velocity is unknown. Acceleration is 3. And time is unknown. You can find out how long it takes to go the 10 meters, and you can find out how fast it's going at the end of the 10 meters. Does that mean you need to do the motion problems? There's absolutely nothing wrong with you having a motion equation problem tomorrow. Eventually, the box encounters an area where the surface is rough. This generates a frictional force that is 40% the size of the normal force. What is the size of the frictional force? Friction equals 40% of the normal force. I'm very unlikely to say that. I'm probably just going to tell you what the coefficient of friction is since we've used that word. 70 newtons. How does this affect the acceleration of the box? I don't know. I'll have to figure it out. But I'd argue that there's now a new force acting in the system in this direction. So it's horizontal. So I'm thinking it's going to be 50 cosine 30 degrees minus friction equals ma, which means 43.3 minus 70 equals 15 times a. That means a is negative 1.8 meters per second squared. That seems like the box is now slowing down. There's a new acceleration. It is in the opposite direction. That must be slowing the box down. Testable tomorrow? Yeah, why not? I see absolutely no reason why this shouldn't be on the test tomorrow. Go ahead.
Where did you get that? Like extra? How'd you know it was? Oh.
I've given you an entire test of practice problems, right? You want more, but I'm not sure what more to give you. I would say that first, by noting how many of you are writing down feverishly during this time, you didn't do this problem. That says something. I would have. It is the practice test. And if you didn't finish in class, last night would have been the appropriate time to do that. I do understand that it is Spirit Week. Don't know what to tell you. You don't have the test on Friday, though, do you? We're going to have the test. We have to. So you're going to have 2 problems tomorrow. I can guarantee you only a few things about them. One, friction will play a role in the problem you have tomorrow. You should expect that. You should be able to draw a free body diagram. That's definitely going to happen tomorrow. And you should be able to manipulate your free body diagram by applying a coordinate system and being able to take one of the forces and break it up into its components. These are all the things we've trained for. You should be able to apply Newton's first law and second law to it. There will be 2 versions of this problem, but in all versions of this problem, you will have the same number of forces, and at least one of them will be off axis. So everybody will be required to deal with a force that has to be broken up into components, and everybody will be required to set one of their directions equal to 0 and one of their directions equal to ma. You should expect that I am going to use the coefficient of friction in the problem. You should expect a verbal problem where you'll have to give me some expository answers, paragraphs. Make sure you answered the questions that I ask. And if there's more than one thing that I'm asking for, make sure you address each item. Even if you address it incorrectly, at least try to address it. I think it's very likely that the expository question is going to focus on static friction and the implications of an inequality. The multiple choice, I am going to try and trick you. There's no doubt in my mind I'm going to try and trick you. Remember questions like, if you throw a ball into the air, when it reaches its highest point and the velocity is 0, is the acceleration 0? Many of you still will say it is, but it's not like gravity turns off. Well, there's force versions of those problems, so expect me to try and ask you force questions that are like that. However, you also need to remember that the multiple choice retroactively goes back to the beginning of the year. So there will be motion problems in the multiple choice. There can clearly be motion problems in the FRQs too, but I really don't want to highlight that as we have limited amount of time. I suspect that each of the FRQs is going to be somewhere around 10 to 12 minutes each, and the multiple choice is going to be about 10 to 12 minutes. There are 10 multiple choice questions. I'm trying to set the test up to be a 44-minute test. It's right now 3 pages, but I'll be printing out 5 of them because one of them will be your equation sheet, which you will now be able to use on every test after this one. All right. So you asked if I can provide you with more practice. I don't know if I can or not. But let me throw it back at you. What if I provide more practice and only 3 kids do it? I don't know if that's been an effective use of my time. But I will attempt to come up with a practice question.